Hi, all CHEMMaster followers. Hope you all preparing well for upcoming chemistry competitive examinations. So here I can say it is up to you. You can join or not on chemmasters.online for the concept courses, or you may practice or not on our online test series from chemmasters.online. But watch the videos on CHEMMaster YouTube channel completely. I can say and I can guarantee that each and every video will give you the most valuable content. Okay, right. And here these questions are picked up from stereochemistry-asymmetric synthesis exam, which was conducted on online test series of chemmasters.online. Okay, right. Now, to solve the questions on stereochemistry, one should have basics to advanced concepts and one should have great imagination power. Okay, most of the transition states in stereochemical questions deals with 3D imagination. Okay, so here one should practice more and more on stereochemistry question, then only one can solve a stereochemistry problems accurately. Okay, now try to look at the given question. The major product of the following reaction is. Here, if you look at the given reagent, we have given with Wilkinson's catalyst. Okay, and we know that Wilkinson's catalyst is the most important catalyst for competitive purpose. We may expect frequent questions from Wilkinson's catalyst. Okay, so the hydrogenation in presence of Wilkinson's catalyst takes place selectively on unsaturations of a given organic compound. So here you can see we have cisalkene, transalkene and alpha beta unsaturation. So three types of unsaturations are there on the given organic compound. Then which alkene is selectively reduced by Wilkinson's catalyst? This is the question here involved in it. Okay, to give answer for this problem, we need to have the order of selectivity of Wilkinson's catalyst of alkenes to reduce them. Okay, so this is the order. If you remember this, you can solve most of the questions or most of these kind of questions from Wilkinson's catalyst. Okay, so this is aryl group, which is having highest selectivity, then followed by alkyl group here. Okay, and then so these two are almost the same. The ring alkene here CH2, these two are having almost same rates of hydrogenation with Wilkinson's catalyst. Okay, and next case here, alkene, disubstituted alkene, right? That is geminal disubstituted. And here, cis alkene is having great, that means higher selectivity than trans alkene. Okay, which is having higher selectivity than tri-substituted alkene. Now, by just looking at this selectivity order of Wilkinson's catalyst, we can simply choose option 2 as the correct one, because cis is having higher selectivity than trans by Wilkinson's catalyst. That's why cisalkene is reduced. Okay, so option 2 is our answer. And next question. The major products X and Y in the following reaction. So the given reactant is having hydroxy group, which is shown as above the plane of the molecule, right? And we have another carbonyl oxygen. So simply zinc borohydride, which is going to reduce this keto functional group, right? And when you see zinc, we know that zinc plus 2 chelates. Okay, so here zinc plus 2 chelate with the lone pair of electrons of these two oxygens, so which can be simply represented here as we have keto functional group here, then here we have oxygen of the hydroxy group. The lone pair of electrons of two oxygens chelate with zinc. Okay, so this chelation leads that the two oxygens are on same plane. Now the hydride transfer from BH4 takes place from any one side. Okay, so if hydride attack from the bottom end, then these two oxygens should move above the plane. If this hydride attack from the top end, these two oxygens should move backside end of the plane. Okay, simply what you get from this, syn product is the major product because zinc chelates with two oxygens. Okay, right, and here option 1 is the correct one. Syn product is the correct one for this zinc borohydride reduction. Now the second case, here we have salt, here what we can say, borohydride with ammonium. Okay, right, and here just to draw the same structure, O here, O minus, which can attack boron, right? In this case, one of the acetate group cleaves from it. So here OAC, and here we have hydride. So from this, what you observe, the hydroxy group directs hydride attack of boron from the side, from its side. Okay, so the hydride attack from here. In this case, the oxygen just moves like here, OH. Okay, right, and here we have, so after further process, okay, so here we have OH. In these two cases, what you can observe, these two hydroxy groups are not in a same plane. One is above the plane, one is below the plane of this molecule. In this case, the major product is anti-product. Okay, so here you can see two hydroxy groups are anti to each other. That's why when you apply NH4 minus NH4 plus minus BH, then we can get anti-product, and when you apply zinc borohydride, you can get syn product as the major one. So option 3 is the correct one. What is the concept involved in this question? The chelation is the main point or key point. Okay, right. And next question. The major products X and Y in the following reactions. So just look at what is the difference in the two reactants. You can simply find that the alkene coordination. So here alkene here on this, and here we have the alkene having that means place changed from 1 to 2. Okay, right. And to give answer for this problem, we need to draw Newman projection, right? So as I said, when you are going to solve stereochemistry problems, we should practice more and more. Okay, then only the transition states can be drawn easily. Otherwise, it will be very difficult. Then you cannot find the correct answer right here. So that is this CH2 is observed here. Now the rhodium catalyst simply interact with this oxygen and also coordinate with this alkene, right? And here you can draw the ligands, remaining ligands. So what you understand from this, the hydroxy group directs hydrogenation and hydrogenation of this alkene from this hydroxy group end. So here the hydroxy group is above the plane. That's why the hydrogenation of this alkene takes place from the above the plane. So in this case, what you find, the methyl group should move back side of the plane and hydrogen just looks like above the plane. Okay, and in this case you find that methyl group is backside because hydrogenation takes place from the front side or from the side of this hydroxy group. In this case, methyl group moves backside end. Okay, listen carefully. Now in the next case, just draw the same here the Newman projections, hydrogen, methyl, here is the OH, and here we can take methyl group, and here double bond which is having alkyl group. Okay, so just draw alkyl group, and here is the hydrogen. Now same rhodium interact with oxygen of hydroxy group, also coordinates with alkene, right? And here we can draw the remaining ligands. Now the same process, the hydrogenation takes place from the side of this hydroxy group, right? And here just do the same thing. Now if you do that, you can get the product like this, where we have hydroxy group above the plane. Okay, here is a methyl. Then here the hydrogen, that means the hydrogen which comes from that hydrogenation should be above the plane, because it is from that hydroxy group end. Okay, and here we can draw methyl group, and in this process the alkene substituent should move backside end. Here is the R, right? And we know that in the representation of final product, the longest chain should be on the plane. So in that consideration, we need to rotate this single bond. So if you rotate this single bond, what happens? So when you rotate this, the that means the backside group just move onto the plane, and this methyl group which is on the plane should move above the plane. Okay, so in this case methyl and hydroxy group are same side or syn to each other. So option 2 is the correct one. Here the single bond rotation is very important. Okay, so from that you can easily find the correct answer. And next question, the major product X of the following reaction is. Here another more advanced question. So we have tin. So we know that tin can coordinate at multiple sites. Just take it multiple sites. So here we have oxygen, oxygens with lone pair of electrons. These three oxygens can coordinate with tin. But here we have tetramethylene diamine. What is the structure of it? Just try to draw. So tetramethylene diamine which chelates with tin. So this chelation effect of TMEDA which changes the transition state, which can be observed here. Okay, here is the benzyl group, and here C double bond O, right? And here OPMB. Okay, so tin chelates with all these. In general case, if TMEDA is not there. Okay, right? And in the here what I said, so just wait. So tin chelate with this TMEDA. So here tin can coordinate maximum with 3. Okay, Lewis what we say Lewis bases. Okay, so in this case here we have OPMB, right? And which is free because it is not going to interact or coordinate with this tin, because TMEDA is there in the reaction medium which coordinates with this tin, right? And now the base TEA. What is TEA? Triethylamine, which can abstract acidic proton from here, and then there is a formation of enolate. So you can see this enolate where the vectors, that is dipoles, are cancelling each other. Okay, dipoles are cancelling each other, which favors enolate. You can see oxygen here, and here OPMB, here is the hydrogen, and here is the nitrogen. Now try to give here on right side, on left side, oxygen gets first priority, nitrogen gets second priority. Here oxygen gets first priority, hydrogen gets second priority. Now 1 1 and 2 2 are opposite to each other. That's why this enolate is enolate. We know that enolates will produce anti-product as the major one, and if we have Z-enolate which produces syn product as the major one. Okay, so the effect of chelation with TMEDA, it is going to produce E-enolate, and that is going to produce anti-product as a major one. And the final stereochemistry is decided by this Evans axazolidine. So Evans axazolidine is very important for competitive purpose, and the stereochemistry of this group affect the stereochemistry of the product. Here benzyl group is backside of the plane. Okay, so that's why PMBO should be above the plane to minimize the steric repulsions here. And whenever PMBO is above the plane, then hydroxy group should be backside the plane, because it produces anti-product from that E-enolate. So option 4 is the correct answer. Okay, so you can get these kind of high standard online test series from chemmasters.online. So we are just working on organic test series now. Already we have more than 15 or 20. Already we have conducted 15 more than 15 online test series. So if you're interested, you can visit chemmasters.online and you can practice very high standard questions, and which helps you a lot in increasing your success rate. And you can also join the best concept oriented courses from chemmasters.online, and they will help you a lot. Thank you very much. And if you like this video, please like and subscribe this YouTube channel, that is CHEMMaster. So as I say, it is up to you. If you are further interested, you can visit and join chemmasters.online, or so please watch these videos. I can say whatever I post on YouTube channel CHEMMaster are very valuable for you. So most of you are not using them properly. Okay, so please use them. They also help you a lot in your success. Thank you very much.